Hello students, and welcome to our next video here for calculus. Today we're looking at exponential rates of change where we have an exponential with a base of e, and I think we're going to jump straight into an example here. I don't think we need to introduce much more in the way of theory because we have done rates of change before. So consider this example here. I've got some bacteria that are growing according to this formula. The population is 4,000 e to the 0.1 t, where t is the time in hours after it started. How many bacteria are there after 5 hours? Well, I've got a formula for how many bacteria we have with respect to time. So I simply substitute that 5, right, t equals 5, into my equation there, and when I evaluate that I get to 3 significant figures, 6,590. Part B says find the rate, right, the instantaneous rate we're going to call this, to B onto T, at which the number of bacteria is increasing, and show that it's equal to 0.1 B. Now that seems a bit curious. We'll get to that later on. But what that's really asking me to do is to differentiate the equation. So to differentiate B with respect to T, I've got this exponential here. Without sort of using the full version of the chain rule, we know that to differentiate an exponential, I differentiate the power and multiply that by the original function. Now the derivative of the power here, the exponent, is 0.1. So it's 0.1 multiplied by my original function. I could say that means it's equal to 400 e to the 0.1 t. But coming back to the question, show that to b into t equals 0.1 times b. Well, remember this here is b, so it is 0.1 b. That's what we're asked to do. Next up, at what rate are the bacteria increasing after 5 hours? After 5 hours, again, I'm after an instantaneous rate. I'm going to use dB onto t, and where t equals 5. So that's one option. There is another option. We'll talk about that in a tick. So dB into t is 0.1 times 4,000 e to the 0.1 times 5, right? We let t equal 5. When I evaluate that, I get 659 bacteria per hour. That's perfectly fine. But remember the previous question and the one before that. When we originally found dB to t, we showed that it was equal to 0.1 b. And I've already found the population at b equals 5. That was part A, I think. So I could, using fewer substitutions, I suppose, simpler calculations, simply go 0.1 multiplied by that answer, which was 6,590. Okay, so more than one way to perform that calculation. Anyway, D, the average rate of increase or rate of change, the average rate of change over a period of time, right? What I want to do is find the change in population divided by the change in time. So I need the initial population, and the initial time, of course, is t equals 0. I need the population after 5 hours, we've calculated that, and t equals 5. So I think the only thing that's missing is the initial population. We've already calculated, or we can very readily infer the others. So substitute t equals 0. My original population is 4,000. So that means my population has increased from 4,000 to 6,590, and it's taken 5 hours to do that. So the rate of change is the change in population, 6,590 minus 4,000, divided by the change in time, which was 5 hours. So it's been increasing at an average of 518 bacteria per hour. Now, we're nearly done here, I think. When are there 10,000 bacteria? So that means that B equals 10,000. We substitute that in. 10,000 equals 4,000 e to the 0.1 t. I need to make t the subject. That's how we solve that. I'm going to divide both sides by 4,000, which means that e to the 0.1 t equals 2.5. Then I do the log of both sides. Okay, the log base e of both sides means that this here becomes 0.1 t, and this becomes the log of 2.5. Multiply both sides by 10 to get rid of that 0.1, and t is 10 log 2.5. Grab my calculator. 10 log 2.5 equals 9.16. Okay, after 9.16 hours, three significant figures is a bit tricky. I could convert that to hours and minutes, I guess, but three significant figures. That'll do us. And I think this is the end. When are the bacteria increasing by 10,000 per hour? Now, I don't want after how long has there been an average increase. I want an instantaneous increase. So dB on dt equals 10,000. Remembering that dB on dt was 0.1 times 4,000 e to the 0.1 t from a previous question, or 400 e to the 0.1 t. Now I want that to be equal to 10,000. Right. So dividing both sides by 400 as we did before, we get this. Taking the log of both sides, I have 0.1 t is the log of 25. Now, the log of 25 is not 10 times the log of 2.5. Okay, we can't take that previous answer and multiply it by 10 or something, or divide it by 10. So, t is 10 log 25. Calculator's going to tell me 32 hours, 11 minutes. That's fairly precise there, I suppose. Okay, that's about it. You can see that we used logs there to help solve an exponential equation on 2 occasions, and we differentiated some exponentials there as well. That's largely going to bring us to the end of exponentials for the time being, and after this we move on to radians and a little bit more trigonometry. Now, if there was anything there that didn't quite make sense, and that could well be the case, make sure that you clear that up in class. Okay, I'll see you there.